A single Chinese province is producing more semiconductor-related engineering graduates every year than the entire United States. If that sounds exaggerated, that's because most discussions about the chip war begin in the wrong place. They begin with export controls, sanctions, or the latest AI processor. Those are visible. Talent pipelines are not. Yet if you asked a semiconductor executive what keeps them awake at night over the next 15 years, many would mention skilled engineers long before they mention silicon wafers. This video isn't about whether China has already surpassed the United States in semiconductors. It hasn't, at least not where it matters most today. The world's most advanced chip design software remains largely American. Extreme ultraviolet lithography is still dominated by a handful of companies outside China. Taiwan continues to manufacture the most sophisticated logic chips on Earth. The question is different. What happens when one country starts producing engineers at a scale that another country simply cannot match? That is a slower story. It attracts fewer headlines. It also has the potential to reshape the industry more profoundly than a single sanctions package ever could. Take Jiangsu Province. Jiangsu is not China's largest province by population, nor is it usually the first place foreign media mentions when discussing Chinese technology. Shenzhen receives more attention. Beijing dominates political coverage. Shanghai attracts financial headlines. Meanwhile, Jiangsu has quietly built one of the world's largest concentrations of engineering universities, semiconductor manufacturers, research institutes, equipment suppliers, and vocational training centers. Cities like Nanjing, Suzhou, Wuxi, and Changzhou are no longer simply industrial hubs. Together, they form something closer to an integrated semiconductor ecosystem. That distinction matters. Building chips is not like assembling smartphones. A modern semiconductor supply chain demands specialists in materials science, plasma physics, chemical engineering, electrical engineering, software development, optics, manufacturing automation, and quality control. One advanced fabrication plant can require thousands of highly trained workers operating around the clock. Factories can be built within a few years. An experienced process engineer usually cannot. According to China's Ministry of Education, engineering has become one of the country's highest priority academic fields over the past decade. Universities have expanded semiconductor programs, while provincial governments subsidize specialized laboratories and industry partnerships. Following the tightening of U.S. export controls after 2022, Beijing accelerated what it already viewed as a strategic necessity, producing domestic talent rather than relying on imported expertise. Notice the sequence. Export controls did not create China's engineering strategy. They accelerated it. That distinction often disappears in political debates. The United States, meanwhile, has responded with substantial investments of its own. The CHIPS and Science Act committed tens of billions of dollars toward domestic manufacturing, research, and workforce development. New fabs announced by companies including Intel, TSMC, Samsung, and Micron represent serious industrial investments. Yet constructing fabrication plants and producing experienced engineers operate on different clocks. Money can finance buildings immediately. Universities cannot graduate senior semiconductor engineers overnight. The Semiconductor Industry Association has repeatedly warned about workforce shortages across design, manufacturing, and equipment maintenance. Multiple reports estimate that tens of thousands of highly skilled semiconductor jobs in the United States may remain unfilled over the coming decade unless education pipelines expand significantly. That raises an uncomfortable arithmetic problem. Suppose two countries both improve semiconductor manufacturing. If one produces twice as many qualified engineers every year, the gap may not appear immediately. 5 years later, it becomes noticeable. 10 years later, management structures change. 15 years later, research leadership begins shifting. Compounding works in education just as it does in finance. One graduating class rarely changes history. 20 consecutive graduating classes often do. This is where I think much of the public conversation misses the point. People naturally focus on breakthrough technologies because breakthroughs are dramatic. A new AI chip launches. A sanctions announcement dominates headlines. A company unveils a faster processor. Those events are visible. The education system feeding that industry is almost invisible until it reaches a scale where ignoring it is no longer possible. Here's the question I keep coming back to. Can the United States maintain technological leadership if it continues relying primarily on attracting global talent, while its strategic competitor increasingly develops that talent domestically at a much larger scale? I'm not certain the answer is no, but I don't think anyone should assume the answer is automatically yes either. Because once a country consistently produces more engineers than its competitors, the conversation eventually stops being about catching up in manufacturing. It becomes a conversation about who will define the industry's next generation. vidIQ. There is a habit in geopolitical analysis that sounds reasonable, but often leads people in the wrong direction. We assume that whoever invents the best technology will naturally dominate the industry built around it. History suggests otherwise. Britain pioneered many technologies of the Industrial Revolution, yet manufacturing leadership gradually spread elsewhere. The United States invented much of modern consumer electronics, but production migrated to East Asia over decades. Innovation matters enormously, but scale determines how long that innovation can be sustained. Semiconductors are beginning to follow a similar logic. Think about what happens inside a modern chip company. A successful processor isn't designed by one brilliant engineer. It is the product of thousands of specialists: circuit designers, verification engineers, materials scientists, packaging experts, software developers, equipment technicians, reliability analysts, and manufacturing engineers all contribute pieces that are individually complex, but collectively indispensable. If even one category becomes scarce, progress slows. That's why China's strategy has been remarkably consistent over the past 15 years. It hasn't focused exclusively on creating the next NVIDIA or the next TSMC. It has spent equal attention building the workforce underneath them. Look at Jiangsu again. Companies such as SMIC, Huatian, JCET, Yangtze memory suppliers, equipment manufacturers, specialty chemical producers, and hundreds of smaller firms operate within a relatively concentrated industrial corridor. Universities are nearby. Research institutes are nearby. Graduates often move directly into local industry instead of relocating across the country. That creates something economists call labor density. The phrase sounds technical, but the effect is simple. When thousands of engineers work in the same region, knowledge moves faster than formal documentation ever can. An engineer changes employers and carries practical experience with them. Suppliers solve production problems together. University professors receive immediate feedback from manufacturers about skills students actually need. Startups recruit experienced workers without convincing families to move thousands of kilometers. Silicon Valley grew this way. Taiwan's semiconductor industry grew this way. Jiangsu is attempting exactly the same model, just with far more government coordination. This is where critics usually raise a valid objection. Quantity doesn't equal quality. They're right. Graduating 100,000 engineers doesn't automatically produce 100,000 excellent engineers. Educational standards vary. Experience cannot be manufactured in a classroom. Creative research environments are difficult to engineer through policy alone. Those are serious limitations, and they shouldn't be dismissed. But there is another side to that equation. Large numbers increase the probability of exceptional outcomes. If one system produces 10 outstanding chip architects every year, while another produces 50, the second system has more opportunities to create breakthrough companies, research groups, and manufacturing leaders. Excellence is never guaranteed, yet larger talent pools consistently generate more statistical outliers. Sports demonstrate this clearly. Countries with larger participation pools don't automatically produce champions. They simply produce them more often. Semiconductors are becoming a similar numbers game. The United States still possesses extraordinary advantages that China has not replicated. American universities remain among the world's strongest research institutions. Venture capital continues to finance ambitious chip startups. Companies like NVIDIA, AMD, Broadcom, Qualcomm, Apple, and Cadence occupy positions that competitors still struggle to challenge. None of that disappears because another country graduates more engineers. What changes is the margin for error. For decades, America could afford periods of underinvestment in engineering education because it attracted talent from everywhere else. The world's best students often wanted American degrees, American companies, and American careers. That model is becoming less reliable. Immigration has become more politically contentious. Visa processing remains uncertain for many highly skilled workers. At the same time, China's domestic technology sector offers opportunities that simply didn't exist 20 years ago. Engineers who once might have left permanently increasingly see reasons to stay. That doesn't mean there is a mass exodus from Silicon Valley. It means the flow is no longer one-directional. I think this is one of the least appreciated shifts in global technology. The competition is no longer just about convincing foreign talent to move west. It is increasingly about preventing domestic talent from seeing better opportunities at home. And that's a much harder contest to win. There's another detail worth considering. Semiconductor manufacturing isn't isolated anymore. AI, robotics, electric vehicles, defense systems, industrial automation, and quantum computing all compete for many of the same engineering graduates. One additional semiconductor engineer isn't just another employee. It's one less engineer available to another strategic industry. That creates a multiplier effect few headlines capture. Which raises another question. If China's universities continue expanding engineering capacity, while the United States relies primarily on increasing productivity through automation, can software compensate for a widening gap in human capital? That's the argument many technology executives are quietly making. The next decade will tell us whether they're right. There is a point where every argument about China's engineering advantage runs into the same objection. If they produce so many engineers, why are they still behind at the cutting edge? It's a fair question. In fact, it's the right one. Because if sheer numbers were enough, China would already dominate every segment of the semiconductor industry. It doesn't. The most advanced logic chips are still manufactured primarily by TSMC in Taiwan and increasingly by Samsung in South Korea. The software used to design those chips is dominated by American firms like Synopsys and Cadence. ASML in the Netherlands remains the only company capable of producing extreme ultraviolet lithography systems at commercial scale. Those are not small advantages. They are the result of decades of accumulated expertise, intellectual property, supplier relationships, and engineering experience. This is why I would be cautious about any prediction that says China will simply overwhelm the industry because it graduates more engineers. Talent is necessary, it is not sufficient. But here's where the discussion usually stops too early. People often compare today's technology leadership as though it were frozen in time. They assume that because one country leads today, it will naturally lead tomorrow. Industrial history rarely works that way. Leadership is constantly being renewed or quietly eroded. Consider semiconductor equipment. China still imports critical manufacturing tools because domestic alternatives often lag behind international competitors. Yet every restriction imposed on those imports creates an incentive to develop local replacements. Initially, those replacements may be inferior. Companies complain, productivity suffers. Then the engineers improve them, not once, every year. This is where annual graduate numbers become strategically important. If thousands of additional engineers enter equipment companies, materials suppliers, chip designers, and research laboratories every year, each generation inherits the work of the previous one. Failures become technical papers. Technical papers become better prototypes. Better prototypes eventually become commercial products. Innovation is usually less dramatic than people imagine. Most breakthroughs are hundreds of incremental improvements stacked together until, looking back, they appear sudden. Think about China's high-speed rail network. 20 years ago, many analysts dismissed it as an expensive imitation of foreign technology. Today, China operates the world's largest high-speed rail system by an enormous margin, exports rail technology abroad, and continues refining it domestically. The lesson isn't that semiconductors are identical to railways. They're not. The lesson is that industrial capabilities evolve, countries learn, engineers gain experience, supply chains mature. That process often takes longer than political news cycles. There's another complication that deserves attention. The semiconductor industry is approaching physical limits in several areas. Shrinking transistors indefinitely is becoming increasingly difficult and increasingly expensive. Future gains may come less from making chips smaller and more from advanced packaging, new materials, specialized AI accelerators, photonics, and three-dimensional integration. Notice what those fields have in common. They're engineering intensive. No single breakthrough eliminates the need for large teams. Quite the opposite. Complexity increases. That could favor countries with deeper engineering workforces. At the same time, the United States has advantages that statistics don't fully capture. American universities continue to attract exceptional researchers. The venture capital ecosystem remains unmatched for turning laboratory ideas into companies. Collaboration between startups, established firms, and defense research has repeatedly produced technologies that looked improbable only a decade earlier. It's entirely possible that one American breakthrough creates another decade of technological leadership. History gives us plenty of examples. But depending on repeated breakthroughs is different from building a broad industrial base. One is difficult to predict, the other compounds steadily. Here's my own view. The conversation has become too binary. Some commentators insist China is destined to dominate semiconductors. Others argue export controls guarantee permanent American leadership. Neither position fits the evidence. The data points somewhere in between. The United States still leads in several of the industry's highest value segments. China is reducing its dependence faster than many expected. Both statements can be true simultaneously. The uncertainty lies in timing. Will China's expanding engineering pipeline translate into world-leading semiconductor companies within 5 years? Probably not. Within 15? That question deserves far more attention than it receives. Because engineering education is one of the few strategic investments where today's policy decisions don't reveal their full consequences until an entire generation has entered the workforce. And by the time those consequences become obvious, changing course is no longer a matter of passing another funding bill. It's a matter of catching up with 15 years of accumulated experience. There is a temptation to measure this competition by quarterly earnings, stock prices, or the latest benchmark for an AI chip. Those metrics matter. They just don't tell you where the industry is heading. A country's technological position is built on layers. Research comes first, education follows, then suppliers, then manufacturing, then capital, then global customers. Remove one layer and the structure weakens. Strengthen all of them at the same time and the effect compounds. That is what makes Jiangsu interesting. Not because one province guarantees China's victory, but because it illustrates a governing philosophy. China isn't betting on one company becoming the next NVIDIA. It is betting that if it trains enough engineers, builds enough laboratories, funds enough research institutes, and supports enough domestic suppliers, world-class companies will emerge almost as a statistical consequence. That's a very different strategy from trying to pick individual winners. Whether it succeeds completely is still an open question. But it isn't irrational. The United States has traditionally relied on a different formula. World-leading universities, private venture capital, deep capital markets, immigration, entrepreneurial risk-taking, strong intellectual property protection, competition between companies rather than coordination directed from the center. That model has produced extraordinary results. The smartphone revolution, cloud computing, modern AI accelerators, and many of the semiconductor tools the world depends on all emerged from that environment. The challenge is that this model assumes a continuous inflow of highly skilled people. If domestic engineering output grows slowly while immigration becomes politically constrained, eventually the mathematics begin to matter. Not immediately, gradually. And gradual changes are the easiest to ignore because each individual year looks almost identical to the last. Then one day the cumulative effect becomes impossible to miss. I think that's where this discussion should become less ideological. Too often people frame this as a contest between democracy and authoritarianism, capitalism and state planning, East and West. Those debates have their place. But engineers don't manufacture chips with political slogans. They manufacture them with knowledge, experience, and years of technical training. If one side consistently expands that talent base faster than the other, policymakers should at least ask whether current education systems are keeping pace. Here's something that deserves more attention than it gets: demographics. China's population is aging. Birth rates have fallen sharply. Over the long term, that creates real constraints on labor markets and economic growth. Some people therefore conclude that China's engineering advantage will naturally disappear. I'm less convinced. When the working age population shrinks, governments often become more focused on productivity rather than less. That means investing even more heavily in automation, robotics, artificial intelligence, and advanced manufacturing, all industries that require more engineers. In other words, demographic pressure may actually reinforce the incentive to develop high-value technical talent. That's not guaranteed, but it's entirely plausible. My opinion is straightforward. The semiconductor race is increasingly becoming a human capital race disguised as a technology race. Export controls can delay progress. Subsidies can accelerate investment. Corporate strategy can shift market share. None of those factors replaces a deep pipeline of capable engineers arriving year after year. If I had to make one prediction, it's this. By the mid-2030s, the defining question in semiconductors won't be whether China can manufacture advanced chips. It will be whether the United States can expand its own engineering capacity fast enough to preserve leadership in the parts of the industry where it still holds a decisive edge. That's a different debate from the one dominating headlines today, and I suspect it's the more important one. One final thought. The next breakthrough processor, the next lithography machine, or the next AI accelerator will probably make front-page news. The university classroom producing the engineers who design those technologies almost certainly won't. Yet history has a habit of rewarding the quiet investments long after the headlines have moved on. If you enjoy this kind of long-form analysis that follows the underlying forces rather than the daily noise, subscribe and join me for the next one. There's a lot more beneath the surface than the headlines suggest.